Hello, my name is Maria Espinosa, and I'm a junior here at the University of Illinois at Springfield. This final analysis of MS, IR, and NMR is going to be for the organic chemistry laboratory. The first thing we're going to do is analyze mass spectrometry. The formula is C6H10. To begin with, we're going to see that we have a base peak at 67, and our M plus is 82, which indicates the molecular mass of our compound, C6H10. Then we have to look at the difference between the important peaks and the M plus. So the first one is the difference between 82 and 41, and minus 41 giving us 41. This indicates the presence of a double bond between carbon and carbon and a hydrogen attached to it, following with two CH2s. But why is this? It happens that the DOU of this formula calculated with 2C plus 2 plus M minus X minus hydrogens, all divided by 2, give us a DOU of 2. Indicated the presence of a pi bond, right, and a ring. It happens that double bond, it is located inside the ring. Then we also look at the base peak and the M plus difference, giving us M minus 15 equals CH3. We're not sure that this is going to be in our compound because, as I said before, we have a ring. So this have to be confirmed with proton NMR. The first step to analyze IR spectrometry is identifying the 5 different zones. Zone 1, as you can see, is from 3700 to 3200. In this case, we don't see any important peaks going on. Then we look at zone 2 from 3200 to 2700. So right above here, there is an interesting peaks going on. The first peak that you see, it is above 3000 just by 64 numbers, which means the presence of sp2. But the other two are located below 3000. This indicates the possible presence of sp3. Since we know that the DOU of our compound is 2, indicated a pi bond and a ring, the pi bond coming from the possible double bond with carbon and carbon, indicating sp2, and then the ring, carbon hydrogen bonds with sp3 hybridization, which is the 2 numbers below 3000. Then we go to zone 3 from 2300 to 2000, but there's nothing important going on. And then we get to zone 4 around here, and then we see a peak at 1692, and this will help us to confirm the presence of the double bond. Then zone 5 from 1680 to 1450, so about here. And also this peak at 1372 help us to confirm the double bond between carbon and carbon. After looking at MS and IR spectrometry, we came up with the formula C6H10 with a DOU of 2, indicating the presence of a pi bond and a ring, with a possible double bond between carbon and carbon with sp2 hybridization, and then carbon hydrogen bonds with sp3 hybridization. Now we can assume that our structure is going to be a 6-member ring with the presence of a double bond, and then we can add the hydrogens to our structure so we can analyze the protein NMR graphic. Now that we have added the hydrogens, we are going to look at the split importance of this image. It happens that for C6H10, when we zoom in the image, there's no clear split importance that matches with our integration. That means that this compound does not follow the N+1 rule. So to do the protein NMR, we're gonna follow the integration above each peak. The first peak that we're gonna look at is the integration of two hydrogens, meaning the presence of a hydrogen in each carbon. So we can match it up in here. And another characteristic of this specific parent is that it is located between 6 and 5. It was deshielded by the symmetry and the presence of the double bond between carbon and carbon. The next two, they're going to be matched with this one. As you can count, 1, 2, 3, and 4 hydrogens matching this integration, and it's going to be the closest one to the double bond, so it's going to be the closest one to the one that it was deshielded before. And then the farthest away from the double bond is going to be the farthest away from the deshielded carbon, matching up the integration of 4 hydrogens with 1, 2, 3, and 4 hydrogens. Now that we have a structure in mind of a 6-member ring with a double bond between carbon and carbon, we can now analyze carbon 13 NMR. We're going to add the hydrogens to our structure and compare all the different carbon environments that the structure has. When looking at carbon 13 image, we identified 3 carbon environments, 1, 2, and 3. The first thing we're going to do is we're going to split our structure around here, followed with another splitting partner around here, giving us 1, 2, and 3 carbons. 1, 2, and 3 carbons. This one has 2 hydrogens attached to it. This one has 2 hydrogen attached to it, and this one has 1, which is the one connected to the double bond between carbon and carbon. I don't know if you guys will remember, but for mass spectrometry, we said that there was a difference between the N+ of -41 showing the double bond between carbon and carbon. If you go ahead and add the 3 carbon molecular mass, we get a 36 plus 1, 2, 3, 4, and 5 hydrogens, confirming a molecular mass of 41. Now that we have confirmed the presence of the double bond, we can now match the different carbon environments with our image. The first carbon environment that we see is this one right here, because it has the double bond, and each carbon in this part of the structure has just 1 hydrogen attached to it, meaning one that was deshielded, so it's going to be the farthest away from the other peaks, matching up with 3, carbon environment number 3. The next one is going to be the closest to the double bond with 2 hydrogens attached to them, matching up with carbon environment number 2. And the last one is going to be the farthest away from the double bond, known as carbon environment number 1. Thank you so much for watching, and I hope you enjoyed it.